โอเคครับเริ่มแล้วโอเคครับ welcome to oh I have to share my bad okayครับ welcome to well this would be our sixth class your sixth class in cognitive human factors in design right and as we made a sort of like cursory outline this class is about trying to apply or trying to introduce you to the concept of the cognitive human factor, right? So if you think about human factors being your height, your weight, those are physical attribute, okay? Those would be considered human factor if you were designing a share, okay? But now we're not designing shares. We're actually designing products, or we're designing communication approach. We're designing an ad campaign. So these are the things that plays not onto the physical limitation or physical attribute of human being, but to the cognitive, okay? Meaning how human being see things, interpret things, feel things, sense things, and ultimately make decision, okay? And again, you can look at it two ways. You can look at it from, if you want to, quote unquote, manipulate cognitive human factor so that you can sell more products, okay? So you would learn about cognitive human factors so you can assimilate that into your design parameters so that you can attract more attention, get more attention, sell more things, and so forth. On the flip side, as a consumer, okay, when you learn about cognitive human factors in design and in particular in communication, then you will become aware of how these factors have been engineered to use, not against you, but to use you to manipulate your feeling, you manipulate your senses of information. And so all these things, you're being bombarded with information, with sales, with politics, and God knows what, okay? So, okay, so you have to be aware of what it is that's being used in a way on the other side, right? On the other side of the program, you are being sold product, you are being convinced, you're being manipulated, okay? Manipulate is a strong word, but it really is a good way of thinking at it, okay? So you can think of learning about human cognitive factor because you are going to be, quote unquote, the manipulator, or you don't want to be manipulated. Okay, that's the whole crux of this course, right? So you're going to learn about the cognitive human factors and how it's applied to various design. Now, in my part, the module, the application again is not to design of, say, products, physical product, but to design of communication device, communication channels, okay? So in particular, communication, and if you want, the focus of this class would be not just communicating any idea, but communicating what the data tells you, okay? So today, whereas last class was about, giving you the tools to do interactive design, so you can play with the design parameters. Today is more about introducing you to the data visualization. Okay. Now, I already gave you a quick introduction about data analytics, right? There are 3 levels of data analytics. Anybody recall from last class? You'd have to look at the mind map. You can look at from last class. If you remember, 3 levels of data analytics. The first level is you just plot the data, and the data tells you what you need to know about your system, your client, your customer, your market, right? So you plot and you get the picture. The second level and the third level is not covered in this class. Well, the second level is when you do some kind of statistical conclusion on it, some statistical testing, causality, normality, whether or not it is predictable and so forth. And the third level is when you use the data to actually train an AI or machine learning model so that it does very more advanced predictive modeling. Okay, so the second part and the third part is not part of here. It's something that I would teach in the data analytics and be part of your machine learning. Okay, so today it's about how can we just take a piece of data, right, and plot it and just give you the picture, right? So the picture supposedly should be powerful in and of itself. Now, the example that I told you, we don't have to go to the Google right now, but obviously the line that I was telling you about last time, right? The carbon distribution in the atmosphere, right? When you track, and I think 5 years ago, it reached 400 parts per million, right? Well, it's not the 400 parts per million that is startling. It's also the fact that you can look at the timeline of this increase, this spike in carbon component in the atmosphere, a greenhouse gas, and it really took a very sharp turn upward, and that coincides very neatly with the Industrial Revolution, right? So Industrial Revolution, as you know, that's sort of like Victorian England. You know about Queen Victoria, right? Very, if you go to London, it's very famous, Queen Victoria and Albert Museum. So during the Victorian reign, that was when the industrialization really took off. And you can take ice core sample from Greenland, so from Antarctic, drill into the core, right? And then you can look at the carbon dioxide component in the atmosphere, and it really took a sharp turn from the Industrial Revolution. So you don't have to do any statistics, right? It's almost like obvious, unless you really want to be a science denier. So yeah, you can do statistical, but it's just going to confirm that, yeah, it is really pretty much man-made, not human history, but man-made from the industrial age. Okay, fine. That's what we want to talk about. Now, let's think of last time when we did this design experiment, right? Well, I was showing you that you can play with shape, yeah, color, perspective, right? So those are design parameters. So the first thing we're going to do today, right now, is think about design parameters vis-a-vis data visualization. Okay, so before we do that, you have to understand what's data visualization, right? Well, you've been doing that since grade school, probably. Data plot, correct? Okay, let's start with that. Grab this. Now, let me open this page. This is where the okay. Oops. This is being okay. So this is a page that that I'll be using to guide. So if you can see a little icons, right? You can see the icons. This corresponds to different design. Okay. Again, this course is about design, right? If I'm designing a cylinder, what are the parameters? The height, the diameter, correct? Well, in all of this different design of the data visualization, there will be associated parameters. So for example, if you're talking about just a simple scatter plot between X and Y, well, where do you start plotting? From the minimum value of X and Y or from 0? These are all the design parameters. Okay. Why do I, make a big fuss? Well, because you think that it's obvious to present the data, we just plot X and Y versus X versus Y. You don't realize that people who did the X versus Y already thought about the design parameters to influence how you interpret the result. One of the easiest way of manipulating your emotion is, anybody? Well, if I want to sell you 2 computers, right? 2 computers processing. If some kind of rate of flops or floating operating points per second. If I plot from 0 and a bar chart, okay, I'm just using my hand here, just simple, okay, between 2 brands, you can't tell the difference. But if I'm trying to sell, right, if I'm trying to say that mine has lower performance than a competitor, but it's insignificant, I will plot from 0. But if mine was better than the competitor, and I want to say, wow, it's such a big deal, it's a really big difference, would I start plotting from 0? No, I would actually plot just the top so that it emphasizes the difference. Okay, so just a simple, where is the origin? Is a design parameter that takes into account cognitive human factor. Okay, and you as a designer have to be conscious of this. You as a consumer have to be conscious of this. Okay, you see this all the time in advertisement, right? Whenever they want to say this is better than the other, you look at the axis, something like 512 is better than 510, but you start plotting at 505. It looks a big deal when actually it's barely discernible. Okay, so that's the theme that I'm going to. Okay, now we will not be able to go through all of this. Okay, all of this, but instead, okay, so these are all the tools, by the way. What's cool about this page is that when you go to say, okay, let's say you go to pie chart, you would see example and how it's used, and then maybe some fun case or options, and these are all the design parameters that you can play with. Okay, so this kind of help page, tutorial help page, gives you all the options, but the options, how you use them, that's your thing. Okay, that's your thing. You want high contrast, you want low contrast, you want to associate good feeling with the color red or blue or whatever. Okay, you notice that American presidential candidates, they only wear like 3 colors necktie. You notice they never wear more than 3. It's either red, blue, or some kind of I don't know. Yeah, I think just red and blue. Sorry, just 2 colors. Okay, just 2 colors. So these are conscious decision design, right? This same thing here. Okay, so again, you are not going to be taught how to do individually one of them, every one of them. In your project, which is next week, you can explore. Okay, so let me, by the way, let me ask you quickly. Do you guys feel like you want to use the same group, or do you want to reshuffle? Who would prefer? It doesn't matter to me. I think reshuffling is good, but if you want to work with the same because you already had like a line group or something like that, that's okay with me. So the group project for say next week assignment, I'll let you decide on your own. Okay, you're an adult, you can manage. Just let Dimutu know what you decided. Okay, fine. Okay, so instead of going through individually all the different graph modes, okay, I'm going to go to the sort of like conceptual principle. Okay, and these are sort of like conceptual principle, but they are useful as in a way like a checklist. Have you thought about this? Have you thought about color? So if I say number 1, color, number 2, length. So your checklist use of it would be, in this design, have I thought about the color? Okay. Have I thought about the length and so forth? Okay. So let's go to conceptual. Okay. There are 3 things. Okay, there are three things, and this is well, I like to say this is something that you're going to be tested on the exam. You have to memorize these three things because these are the three main things you have to consider. Okay, main things. First, okay, what is it that you are getting across? What comes across? Okay, so again, visualization is part of communication. Okay, so the idea is, what is your design intent? What are you trying to get across? Now, I already mentioned this in a very simple case, right? My design intent is to say my computer processor is, even though it's a little bit slower than the competitor, virtually no difference. That's my intent, right? I want to communicate sameness, right? On the other hand, if I happen to have a faster processing chip to sell, I would try to emphasize that, oh, this is game changing. The speed of my processor is so much faster. You need this for gaming. You can't do this. You're gonna be a lousy gamer if you don't have this processor in your GPU or whatever. Okay, so the design intent, basically, they're roughly, okay, and I'm putting this in a quotation. There are two things that you kind of consider along these two axes. One is, do you want to communicate sameness or difference? You wanna, are you highlighting that yeah, everybody's the same or everybody's different? Now notice this sameness and difference is underlines most of the message. Think about it, and this is not about visualization. If I want humanity to be cohesive, right? Everybody to love one another, I would say that human beings virtually share all the genomes, right? Whereas if I want to highlight the difference, well, I don't want to highlight the difference, but there's certainly you can do that with you know, a racist ideology, try to highlight the difference, like, you know, Chinese people are not the same as Japanese or something like that. You can do all kind of stuff. So this is really the design intent, okay? So in commercial application, in social communication, these two are basic, the bread and butter of the design intent. So let's look at, okay? Now, let me put a little bit further. There are two things that you can talk about in terms of sameness or difference. One, again, one is profile. Again, if I want to say that all Basai students are the same, then I would show that, you know, you have basically same height, same weight, same socio-economic background. Okay, if I want to make the difference, highlight the difference, I'll say, well, you actually a very diverse group. You came from diverse economic background. You live in different parts of Bangkok. Oh, this is a great diversity of student I have. Okay, so it's about comparing profiles. Okay, profile is another one word. In mathematics, sometimes in data science, you use words like attributes. Same word. Profile, attributes, characteristic, demographic features. These are all interchangeable. Okay. Now, the other one in terms of sameness and difference is the sameness and difference in behavior. And this you will see a lot more in time series. And when we go to actual example, you see. So for example, I can plot price of Bitcoin versus price of other speculative asset, say maybe platinum. Okay. So I can try to say that, you know, if you look at it, people who are speculative in Bitcoin, they're also speculating in platinum in the open market. Okay. Or if I want to communicate the difference, I'll say, well, hey, look, Bitcoin is everywhere, but if you invest in real estate, it's very good. You know, Bitcoin just been head diving in this period, but you know, real estate holds value. So it's not the sameness in profile, but it's sameness in movement. Okay, in particular, time series numbers, time series. And this is like the bread and butter of financial econometrics. Okay, you do all kind of stuff, you know, causality test, correlation, rank correlation, I do, you know, I one of the largest project that I was commissioned, it really is about financial markets. So really it's about this kind of thing, except not just the different, but in terms of how they link to one another. Okay. Now let's go to the other one. The other one is not, if you think of sameness and different, it's sort of like A and B, right? A and B, product A, product B, kind of like equal footing. You want one to be better or difference or not the difference, that's A and B. The other one is a little bit like looking at something versus the population. Okay, so the design intent here is to communicate the sense of norm. You know what norm means, right? Norm. Okay, so peculiarity, right? Peculiarity, norm, right? And to this, I'm just going to give you two words, okay, that tends to work. One is called bell curve. What it means is this. What it means is bell curve is, I guess from statistic, you kind of understand that, right? Bell curve tells you where most everybody is and who is outstanding. A lot of time, this outstandingness is a good thing. For example, on an IQ curve, I would like to recruit students on a high end of the IQ, let's say, something like that, okay? So this is kind of like normal. It's still normal, okay? Everybody under the bell curve, there's no freak here, nothing abnormal here, okay? But some of you are smarter than the other. Some of you are taller. If I want to build a épée fencing team, I would try to recruit guys who have long arms, right? Not freaks, right? Not abnormal human beings, normal human beings, but on the long arm side of the distribution. The other one is different. The other one is called anomaly detection. Okay, anomaly detection works in things like fraud. So when something stands out, it stands out for a reason. It's not normal. It's not you have a normal length arm, but a bit longer. So I'll recruit you to my fencing team. No, it's you have abnormally long arm. Now in physical characteristic, that doesn't happen very much. But what does happen? Frauds, right? So for example, if I look at all your, say, transaction, okay, transaction using apps or something like that, right? Now, everybody would have a similar kind of thing, and all the days would be kind of similar, but somehow, let's say on the 27th of last month, you have extremely outstanding number of transactions. Money in and out, in and out, in and out, way higher than your friends, way higher than every other day. It turns out that, let's say, that day coincide with some kind of I don't know, football match. This will be indicative that this is not just more than usual. This is you actually setting up a betting house, right? So authority would do this. Okay. Some of the analytics that I was working on when I was with the bank is about anomaly detection. Okay. So I just give you in the old days, bank would detect frauds because they know the pattern. They know the pattern. Like if a bank teller would sort of like keep some of the clients' passbook and do unauthorized withdrawal or something like that. So you know this kind of behavior. But modern data analytics, they don't do it this way. They don't try to track a pattern that's well known. They try to say that anything that's out of ordinary, okay, we investigate. Now, it may be legit, but if it's so weird, you have to look at it. If there's so much transaction on the 27th of August just for your account, and that happened to be one day after world, I don't know, okay, football, whatever, okay, it's worth investigating. It's worth investigating, okay? So the norm peculiarity, you can think of it as two cases. One is, yeah, it's still normal, still normal. The other one is, hey, something is not right, okay? Something is fishy here, okay? So that's the design intent. You want to communicate with data. Now, let's go back to that carbon dioxide concentration. What am I trying to do? Right? I'm trying to communicate difference, except this difference is not A versus B. It is concentration in part per million before, that's my A, Victorian industrialization, B, after. So it doesn't have to be two different things, right? It could be before and after event, that sort of thing happens as well. So it's still A and B, okay? Now, in that case, yeah, when it's a difference, it's alarming. It's alarming, okay? And in a way, you can think of it as, well, are we saying this is the norm? And that's why you hear this word in political science or in news class. Is this the new norm? What it means is that if you were, well, this is not a great example because carbon dioxide measurement is only available retroactively. So that Victorian time, they were not aware of this. But let's say that you could monitor carbon dioxide concentration in the atmosphere in real time, and you could do this back when Queen Victoria was alive. Okay, you can see that it's low, it's low, it's low, it goes up, it goes up, it goes up, it goes up. At that time, this would have been anomaly detection problem. This would have been an anomaly detection problem. Okay. And of course, because you can't do anything about it, this anomaly became the new norm. Right? But you can, yep. Yeah, definitely. Definitely. For example, the new norm could be like short-sightedness in people. This is definitely a new norm that got established fairly recently. So before that, when most of the children didn't even go to school, went farming, they didn't get really short-sighted that much. So if you track the percentage of short-sightedness in children, right, there's a big curve when you have this formal schooling, and maybe there's another big jump when you have this smartphone. I don't know. Okay, so we'll see about that. Right. Good point. The idea here is that you plot the picture, you get the message, you get it, okay? And how it's explained is later. Now, second intent. Now, this is a little bit less trying to convince. This is just trying to convey the size, right? Communicating size, how big, how small. That's it. So your design parameter here is just big or small. Now, this is where I actually go to some length here, okay? This is something that I teach everyone, I guess, year one, but it's so weird. It's so simple a lesson, and yet very advanced data scientists working for me sometimes forgot all about it. And they make some silly analysis because they're not mindful of this. And this is called what's called number scale, okay? Number scale, if you think roughly, you can break down into categorical and numerical, okay? Numerical means something that's naturally represented by a number, all right? Categorical means, well, you can put a number to it, but it's not natural. For example, your student ID, is that a number? Yes. Is it natural? No. I just happen to force it onto you because, well, I don't want to write your name. So I just use a student ID, which is numerical, but it's not natural, okay? Now, the categorical and the numerical separate further into two more things, okay? So these are the 4 scale, okay? 4 scale. 1, nominal. Nominal comes from the word name. Same thing, same word as the word name. Nominal just means different, okay? Mathematically, you just say that A is not the same as B, okay? So you have different student ID. That's it. You are different. That's it, okay? Now, this student ID does not give you any more information. Well, in Basai case, it does because it actually gives you the order of being admitted. But let's say it's completely random, okay? So how do you communicate? What are your choice? Well, if it's fundamentally nominal, you should represent it intrinsically with either colors or shape. right? Colors or shape, because you don't want to say that, say boy would be shape. When I say shape, I also include symbol. So boys have this symbol for male, right? Girls have symbol for female, right? But how would you feel if the symbol for boy is number 10 and symbol for women is number 5? Like boys are worth twice as much as girls? That's not good. Or boy is +1, girl is -1. That's even worse, right? So you don't want that. So fundamentally, as much as you can, the neutral message is, well, just different colors, right? Maybe boys blue, girls is red. Although I told you, right? I think I may have mentioned this in the first class. If you go back about 300 years ago, boys would have been represented by color pink and girls would have been represented by color blue. Okay, never mind. But the point is they're different. And you can't say blue is better than red, red is better than blue. Okay, same with the shape. Now, the other one is still categorical in a sense, right? But it's ordinal. In other words, there's some kind of ordering. So not only can you use the sign A equal or not equal to B, you can say A is better or worse than B. This would be something like a beauty pageant, right? So when I say the most beautiful, whatever, contestant wins the crown, the second most beautiful is the runner-up, first runner-up, third most beautiful will be the second runner-up. But that's all you can say. You can say that this one is more beautiful. Can you say how much more? You can't, right? Let's say Miss Argentina wins and Miss Somalia came second and Miss Thailand came third. Can you say that the difference in beauty between Miss Argentina and Miss Somalia is the same thing as the difference between Miss Somalia and Miss Thailand? No, you can't, right? You can only say, okay, well, in this case, A, B, C. It's like that. So it's an ABC scale, okay? Again, color. Except in this case, you tend to use what's called color spectrum. And in mathematics, I will show that. Something like an option, color rainbow from red here all the way to, that's kind of like graduated color. So it's not jumping all over the place. Now, more interesting. So how about interval scale? Interval scale, this is where you can measure the difference. So temperature is one of those things where it's a difference, right? You can say this is 25 degrees, this is 28 degrees, so the difference is 3, okay? However, there's no absolute 0. Why? Because, well, in temperature, the absolute 0 is 0%, 0 Kelvin. But in centigrade and in Fahrenheit, they don't have the same 0, right? They don't have the same 0. 1 0 is, for centigrade happens to be relative to water freezing. But 0 for Fahrenheit is below freezing. So it's not the same 0. So you can't divide, right? You can't say this is 3 times as big. So if I say this room is 25 degrees, the other room is 50 degrees, right? And I said that room is twice as hot. Okay? That seems like makes sense. But if I did the same thing in Fahrenheit, it would not be twice as hot. The ratio would be all messed up, right? Because you have different 0. So that's why it's not called ratio scale. You can only do ratio if you have absolute 0. Okay? Now, sometimes you have negative, sometimes you don't. The point is not negative or not negative. The point is, do you have a 0? If you have absolute 0, you can do ratio. Your height, for example, is good. Because I can say somebody who's 6 feet tall is 20% taller than somebody who's 5 feet tall. I can say that absolutely. Because if I mapped it into a centimeter, I get the same ratio, right? So beware of this. Now, most of this would go into some kind of axis plot. And that's what the example will go to. Now, this is something that I'm going to talk in briefly because you might not get the picture. But sometimes you have to be aware of numerosity, meaning just number of stuff. Are you trying to show one thing? Are you trying to show 2 things? That's A versus B. Are you trying to show a handful of things that you can examine in detail? Are you trying to show many things, but still conceivably can look at them individually? Or you have so many of them, like 1,000 data points. You can never look at individual data point. You can only look at like a histogram, okay? And this would influence your design choice, but a lot of times this is rather obvious, so. Okay. Now, I mentioned about the axis, right? The origin, we talked about that, and so I'm not gonna cover again. So again, having a zero, starting at zero or not starting at zero, you don't have to start at zero, but you have to be clear about it, right? You can't just say that, oh, my processor is twice as fast because, you know, I'm just showing the last 1,000 flop. That's dishonest. The other thing is called marking. Now, this is something you're not familiar with, because most of the plotting you've done all your life is linear. In other words, X is linear, Y is linear, okay? There's such thing as a logarithmic scale, and there's this thing called power of 1 to 5 marking. So in other words, I would mark something like 1, 2, 5, 10, 20, 50, 100, 200, 500. Why does that make sense? If I want to separate income into bucket, you would realize that people, if you use a linear scale, right? If I use a linear scale, you make 0 to 50,000, 50,000 to 100,000, 100 to 200, 150. That's not going to work because it's going to be very far. But if I go something like 0 to 10,000, 10,000 to 20,000, 20,000 to 50,000, 50,000 to 100,000, 100,000 to 200,000, 200,000 to 500,000, 500,000 to a million to 2 million, 2 to 5, 5 to 10 million, 10 million to 20. You are going to get more reasonable display. Okay, so 1 to 5 is the reason it's nice is because, well, 1 to 5, these are nice, easy number to work with, and they roughly correspond to logarithmic or exponential progression. So if I plot 1, 2, 5, 10, 20, 50, 100, 200, 500, that's going to track almost like an exponential function. Okay. So this a little something that you should be sort of like, this is kind of like a checklist if you are a professional. So you try to communicate the size, right? What else? Now, this is very important. The last thing that you have to consider, conception. So the first one is like a message. What are you trying to say? The second one is you're just trying to measure this, convey the sense of size. And the other one is you have to be aware that you have to maintain clarity and orientation. Okay. So in this case, it matters how you put legends, label. Are you going to do 2D plot, 3D plot? Does it work with still picture, or can you go with moving, static, interactive? So these are all, you know, design parameters that you would experiment with. But this is about maintaining clarity. Okay. And in label, I would put things like font size or font colors in there as well. Remember, I told you guys that the first project 2 weeks ago that you showed to Ajahn Sarashai, very nice work, but you have such a tiny font, nobody in the back can see. Okay, right. So now that's about visualizing data. I'm going to talk a little bit about visualizing science because, you know, some of us are in a high-tech area. Basically, there are kind of like 3 scales we are operating on nowadays. That modern visualization, computer-driven visualization comes into play. One is like astronomical scale. Okay, this is like astronomy. By the way, do you know about all those pictures from Hubble telescope? You've seen that, right? I mean, you have to be fairly educated. Okay. They look very nice, right? All this faraway galaxy has very colorful. Do you know that those are artificial colors, right? Because what they have is what we call radio astronomy. In other words, they don't look at the picture in visible spectrum. So they have to do a little bit of mapping. Like for this spectrum of the radio frequency, it will be red. For this spectrum, it will be blue. This spectrum will be green. If you look at radio astronomy data, there's no color in it. Okay, so those are the very large. Then you have Earth scale. So there's a lot of this. So this is satellite imagery. This is very important. By the way, I'm going to give this to you, and please use this as your resource. In other words, go to all the link that I gave you. These are all very powerful repository of things you can play with. So for example, your visualization. Okay. So this would be like, so all this example you can play with. And one of the really nice database is from NASA, okay? NASA is very generous. Well, obviously it's publicly funded, but even though NASA is very much focused in space, a lot of image they provide for us for free are Earth, what's called Earth observatory data, okay? These are satellite image. These are things that is quite amazing. I mean, this was not available to people my generation. So this is very high resolution, very clear. It's wonderful. And you can do a lot of things. For example, I don't know how many of you are going to sustainability track, but if you go to sustainability track, mark this web page, because the satellite imagery or satellite image of, say, Thailand or whatever is very detailed and multispectral, meaning that it contains information about atmospheric composition. It contains information about humidity, right? So when you're talking about sustainability of an ecosystem, sometimes you have to look at other spectrum, okay? That, you know, that is, it's not just what the land looks like from the satellite, but the humidity, PM, for example, PM concentration is one of those things, okay? PM 2.5 concentration. So all this is very multispectral. So this is very useful. I would encourage maybe for next week, one of the two team might look at this as a database. Is very good. Okay, let's go back. Okay, now cross astronomy. Now, finally, the very small, and this is very fun. Now, this is a little bit, it's not data visualization per se, because it's more like a representative, right? So all this thing, you can look at, this is very highly elaborate 3D animation. One of the coolest thing is, for example, you know, look at, so for example, well, it looks at the protein spike. Yeah, this is actually a 3D model. Usually the scientists, they use what's called, you know, X-ray crystallography, all kind of advanced technique to do the to do that data. But once they do the data, they can visualize it and say, okay, you guys know how the vaccine work, by the way? mRNA. You know how the mRNA works? Okay, well, imagine that this is a coronavirus, right? mRNA actually is genetic instruction so that your cell produces part. In other words, the blue part. If your cell can produce the blue part and float it around your body, it can't do any harm because it's not a virus. But your antibody or your white blood system start to recognize that there's something weird we haven't seen before. It has this blue shape. And the built antibody start to build things that can latch onto it and digest it. So next time when this actual virus enters the body, it has got the same blue part that your body has already seen before, right? So it latches onto that and destroys it. That's how mRNA works, by the way. Now, what about other vaccine? The weak, they just use actually real virus that are dead or weakened, okay? So actually the whole thing, but no longer harmful. Okay, so something like this. This is very interesting. So I'm just gonna give you a link to it, and okay, so right. Okay. So that's that. Okay, that's that. Now, let's go to, oops, number 6, right? Okay. Oops, sorry. Okay, let's go to the practical bit. Okay, now this is where we start to have fun. Now, again, all this correspond to those little icons that you see. Okay, all I want to do is give you a category. Now, those of you who like to ask what's going to be on the exam, I'll say, okay, can you name all this? Okay, right. What is point plot? What's point plot? Plotting points. Okay, let me show you an example. So, what's the limitation, guys? What's the limitation? What's always the limitation of a visualization? Dimensionality. Okay, so chances are you can only plot in 2 dimensions or 3. Okay, but even 3, that sometimes is clumsy. But this is where I would give you example of this. Now, because these are relatively simple, I'm not gonna demonstrate for you guys, but you can play. So this is all the list plot or list point plot. That's a good one. Okay, so you can watch this in whatever 3-dimension or whatever, right? So, okay, now this just look at this one. That one. This one is created by a function, so it has a pattern. But in real life, you're talking about looking at the data, it would be something like this. Something like this, okay? Something like this. So imagine that this is a very clever thing. Let's say that this is a name, right? This is a name, and this is a height, this is a weight, this is an age. So you can imagine that, again, think of numerosity. If you have 5,000, can you see 5,000 of them? No, but 50, maybe, okay? Would you use this to represent 1 or 2 data points? No, right? So this numerosity thing that I told you, it's a trivial example, right? But you can see why it works. If you have 1 point, you're not going to use this. If you have 2 points, you're not going to use this. If you're going to have a handful of points, yes. If you have hundreds of points, yes. If you have 2,000 points, would you do it? All right? No, you sometimes you do what's called point cloud. It looks like a cloud and it kind of looks nice, but essentially you can't have this. First of all, you can't name this thing. Okay, now I'll show you a segue because this is something that I did. Okay, a good example. Now I'm not showing you how it's done, but here's a good example. Okay, here's a good example. This is all the mutual fund in Thailand. Well, not all, it's only 100 of them. Okay, I can also do this for 500. Okay, virtually all the Thai mutual fund I can do this, but I wouldn't be able to do this for the whole world, let's say. Okay, so again, these are little point plots. Now, never mind what that means. You're not into finance, so it doesn't really mean. Basically, the y-axis is the return. So the higher, the better. The x-axis is the risk. So the higher, the worse. Okay. So you want to make a lot of money, but you don't want the money to go up and down. So Bitcoin would be like you know, high risk, high return, way up there. So this is actually, this is, by the way, real number. Okay, I just this is real number. Okay, I think it's fairly recent from last year or something. So this is all the, you know, the names of the Thai mutual fund. So you can see that if you buy this thing, it's got low risk, low return, high risk, high return. This one is low risk but high return. But you know, the reason that they are here is because they serve different purpose. So sometimes people would want to buy this because it serves a, you know, financial utility that's not reflected. But with respect to risk and return, yes, I can afford to plot every single point with the name, right? Because here it's only 100, fine. Okay. So, and that's one example, right? So this is point plot, right? Literally putting points on the 3-dimension or 2-dimensional axis. Number 2, okay? Point plot. So these are the resource page. You can click to here. You can search them, but you know, I put them here. The other one is called array plot. Now, array plot is very popular now because what it does is you take in matrix algebra, right? If I line you up, okay, how many of you are there? Let's say 50. If I line you up 50, all your names 50 here on the row, and I put your name on the column, and for every pair of student, I put 1 if you knew each other or if you're a friend, okay? That would look a bit like this, okay? Well, actually, it would be an array of numbers. Okay, so look at this screen, okay? So let's say, okay, pretend, okay, look at the screen now. Pretend it's a square screen, a square, not rectangle. And this is student number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, you obviously know yourself, so ignore the diagonal. But if it's 1 or black, that means this student knows that student. So something like this, okay? So this person, 1, 2, 3, 4, doesn't know 1, so it's blank, okay? Now, this can be symmetric or asymmetric. Okay, what's symmetric? What's the difference between symmetric and asymmetric? Okay, is Facebook relationship symmetric? If you are a friend with Bob, is Bob a friend with you? Yes, so it's symmetric. What about Twitter? If you follow Bob, does Bob have to follow you? No. So IJ is not the same as JI. That's asymmetric. Okay. All of this is known as adjacency matrix. And this is a way to visualize. Now, what does this do? In this case, if you look at this, again, we're not doing analytics here. Okay, we're not doing analytics here, but the point is, can you look at it and get the picture? So this looks a little bit random. Well, in fact, it's a random number, right? Okay, so it's a little bit like that. On the other hand, you can see that there's some cluster. Now, I don't have example with me handy, but you can see that in a typical social network, there are cluster. So if you think about it, there is like a rectangle of blacks where everybody knows everybody. And there's another block of black where everybody knows everybody, but between blocks don't know each other, right? So if artificially I say, all of you on the left side know each other, all of you on the right side know each other, none of you know each other, and I line up your student ID starting from the right side to the left side in a square matrix, right? And 1 or black means you know each other. 0 or white means you don't know each other. What are you going to see? You're going to see a big block of black and another block of black. Okay, that, by the way, is called block diagonal. That's very typical of social network. Okay. A lot of time we can do this. We can say, you know, the picture. If I say, how about it? How about this? How about Professor Warasak wants to know if our students know each other really well. And I make this matrix. And this matrix is mostly white. That means you don't know each other. That's like the day one you came in. If the matrix looks like block diagonal, that means you start forming groups of buddies, right? If it's random, then it's almost like a public pace. People just know each other randomly. Maybe that's like after COVID or something. These are visualization of data that immediately gives you the impression or interpretation of what's happening. Okay, so this is very good for social network analysis type thing. Okay, array plot. Okay. So basically, it's looking at the value of the matrix. Now, this one is the staple of statistics. It's called distribution plot. Okay. Now, I'm going to show you later, but you guys know about histogram, right? You've done this. You couldn't have done this with, when you were doing the student project to apply to Basai. A lot of you did this already. Okay, and there's histogram 3D as well. So for example, if I do a histogram of height and weight, I can look at something like this. And okay. Okay. So it's gonna look a bit like that, right? So let's say now let me ask you this: if this x-axis were height, this axis were weight, what would you expect to see? You would expect to see some kind of correlation. So if you look on top, it's not gonna look like a circle. It's gonna look a bit like ellipsoid. Okay. Yep. That's one of those things. Immediately, if I say this is something like how much time you spend studying and how well you do on an exam. If I plot this and it looks like a circle, that means they're independent, right? So how much you spend on studying really doesn't help with getting better grades. If it's positively shaped like a cigar, but positively sloped, then the more you study, the more time you spend, the better grades you get. Now, you can also get a cigar that goes the other way around, right? So you say, well, you spend more time, then you get stressed out and you do worse or something. Okay. Again, the second level of data analytics, you would do statistical tests. Like, is that correlation significant? In machine learning, a third level of data analytics, we would actually put this data to a neural network or a deep learning, and that would make some kind of prediction. Okay, but now, no. Now, we are at the level where look at it and you get the picture. Okay, and the way you do that is by using the right plot, the right color, the right axis, making all the design choice. Okay, that correspond to human being. Now, again, human factors are always part of this. If all of this, okay, why would they make this kind of shading? Why would they make this shading? Why do you think they go to the trouble of make this shading? Because shading in human cognitive interpretation gives you the sense of height. So this gives, right away, I look very far away. If this were not colored and it didn't have the shading, it would be very hard for me to notice that, hey, there's a high peak here. Okay, so a litmus test of whether or not your use of human cognitive factor is successful is, can you get the picture by just looking at it for half a second? Right? If you look at this picture, within half a second, you already get the picture. That means it's well designed, right? It's well designed. So again, ask yourself, right? I walked in your presentation last 2 weeks. I see a whole bunch of text so tiny. Do I get any picture? Do I get anything? No, it's very hard, right? Well, it's that kind of idea. Okay. So this is very good. It's got nice shading, right? Right away. Now this shading, by the way, programmatically gives you a sort of like a lighting location. This is kind of assuming where's the light coming from somewhere out there, right? Now, if I shine the light from here, everything is going to be all yellow or white, right? That's not good. So this again is a design parameter. Okay, it looks obvious to you. Okay, now Mathematica is a little bit of a cheating code because by default, it optimizes the human cognitive factor for you. So you will notice that this function here only say histogram 3D. In fact, there are choices in there about what color to use, what highlighting to use, what is the scale of the plot. Does it go from 0? Does it use log scale? Does it use linear scale? All these are parameters. Now, Mathematica is a little bit of a cheat because if you don't know any of this, you don't want to think about it. It optimizes quote unquote. Okay, by heuristic, it doesn't, So yeah, it's gonna get a nice one. Okay, so chances are, yep. .3D, this has to do with medium. 3D visualization is very intuitive. But for me to actually get more information, I have to be able to play with it, right? I have to be able to click on it. So if I did this, see, for me to get all the information, I have to be able to manipulate it, right? Now, if you think about it, you can't do that with a book. Okay, so in that case, it's better to do one picture here, another picture here. Does that make sense? And then maybe and another one here, like on top, just something like this again. So yeah, 3D is a lot better if you can play with it. But if you can't, well, okay. See, so the perspective of tilting is also a design parameter, right? Now, Mathematica, fortunately, didn't give you this as a default because it's not very nice. So the first one that it gave you is quote unquote optimal, okay? But you can do all kind of things. You can do sort of like perspective, the color and okay. So Mathematica is a good tool. On the other hand, it gives you a false impression. If I give you a more basic language, things like, maybe Python, JavaScript, where you have to specify everything, you will appreciate the pain of thinking all this, okay? So Mathematica is hiding a little bit of a detail. And it's not just hiding for visualizations, it's hiding a lot of things that I use as well. Okay, even machine learning parameters. This is another example. By looking at 2, do you get right away that these populations are different? Right? So you can think of it as, say, height and weight of a blue population and a yellow population, right? So blue population is people who have a wide range of weight and wide range of height, but not so tall, not so fat. Okay, whereas the yellow population very concentrated and very tall and very fat. Right? Do I need to do any kind of statistical testing to give you this message? No, right away it's clear, right? Now, if yeah. So all this and everything else is just feature, just you also remember I told you about design, right? There's a spectrum between design serving a function and just looking nice. Well, once you get the visualization function right, then you can start playing with things that make it look nice. Like, oh, I don't like square. I'm just going to make it round. That's just, okay. That's just to prettify your image. Okay. Doesn't really add anything. This chart element is a cylinder again. Okay. composition plot, this would be like breaking down things. And this is where pie chart beats everybody. Okay, but pie chart is like the mother, the main paradigm of breaking things. I don't have to show you this, right? You know what a pie chart looks like. Comparison plot, well, this is where you do comparison plot. We'll come back to this after the break because this is where I will actually take you through the exercise. Okay, so I'll come back to it. Time series plot, well, that's two kind of thing. One is financial time series, things like financial time series, like the price of gold. You're familiar with that. The other one is sort of like historical timeline, where instead of marking the value, you sort of like mark the time with event. Okay, so these are the two most typical use of a time domain. Okay, maybe I should put here as time domain plot. Vector field plot, I'm going to just mention it. You're not going to use it very much. This is something that I use in physics, right? Do you guys know what a vector field is? Well, you guys live in 3 dimensions, right? If I take a temperature here, there's a value here. So think of a number that floats here. There's a number like 25 degrees floats here. And I take another temperature, maybe it's a bit warmer, so it's 26 degrees here. Okay, so every point in 3-dimensional space, there's a number. Okay, what if every point I take both the temperature and humidity? I have 2 numbers. 2 numbers already is a vector. So if I take the measurement of all those points in this space, it is a vector field. Okay, now the most useful or familiar vector field that you have in real life that you are going to run into, pretty much the only vector field you see is wind speed, right? Right now, wind is flowing like this, and it is 5 miles an hour. So there's a little arrow going like that. Over there, it's near a tornado. It's 25 miles an hour that way. So it's a big arrow that way. Okay, that's a vector field. So vector field you would see, unless you're in science and engineering, chances are you just see in weather report. Yeah. Again, it's one of those things where you look at the picture, you know, there's a hurricane coming your way, right? Okay, so the design of that is very much to grab your attention. Yeah. So with that, let's take a toilet break for 5 or 10 minutes. When we come back, have your Mathematica up. We'll go through this as well as from last class as well. So the second half is going to be a lot more hands-on kind of thing. Okay, Kap, see you in 5 minutes, 10 minutes.